Good afternoon, everyone. In this video, we want to show how one can compute the moment of inertia for a lamina about an arbitrary axis. Now, mass can be thought of as a characteristic of matter that resists acceleration. So we see from Newton's law that to change the velocity of a mass, a force is required. Moment of inertia is considered the rotational analog of mass, it being the characteristic of matter that resists angular acceleration. So notice to change the angular velocity, a torque or twisting force is required. Now, if we consider a point mass for a moment rotating about some axis, the moment of inertia for that mass is computed as the product of the mass times the distance to the axis squared. And here we're using this letter symbol uppercase I for moment of inertia. Now, in the case of a lamina, for example, this rectangular lamina that we show here, to compute the moment of inertia for this about some axis, we're going to consider the lamina to be a continuum of infinitesimal masses of quantity dm. So to compute the moment of inertia, we take each infinitesimal mass multiplied by the distance squared to the axis that we're using, and then you sum all of these up over the region occupied by the lamina. For example, to compute the moment of inertia about the x-axis, well, the distance to the x-axis is given by the y component of the mass. So this is the formula that's going to give you the moment of inertia about the x-axis. And for the moment of inertia about the y-axis, the distance this particle of mass is from the y-axis is given by its x-coordinate. So we take x squared multiplied by each mass, add them all up over that region. Now we also want to define something called the product of inertia. So it's like these two integrals above, but your integrand is the product of x times y, again times dm. The significance of this product of inertia we will discuss in a moment. Okay, now here's our setup where we can find the moment of inertia for a point mass about some arbitrary axis. We'll look at this first. So first let's notice that our point mass is located with the position vector r, x, y, and the z component is 0 as this mass is on the xy plane. Our axis is defined by a unit vector u going in the direction of our axis. So here it is, our unit vector, the direction being theta. Now, we're saying arbitrary axis, but we mean an axis that's going through the origin. So, to find the distance between this mass and this axis, we construct this triangle. And we see that the angle between these two vectors, alpha, that this distance is the opposite angle to alpha. So that distance, we're using d now instead of r, that distance is the hypotenuse times the sine of alpha. Now here's a key step in our derivation. Since u is a unit vector, I can insert the magnitude of u here without changing anything. And then we recognize this expression as being the magnitude of the cross product of u with r. So how we're going to find this distance right here is by evaluating the cross product of these two vectors. Here's how we can compute the cross product. The vector r is xy0, position vector for the mass. The direction vector for our axis is cosine theta sine theta 0. And computing this cross product gives you a vector 0, 0, x sine theta minus y cosine theta. And it's the magnitude of this vector that we want. So we just take this, the absolute value of this component. So that's our distance. Now in computing moment of inertia, we need this distance squared. So we square this expression to get the distance squared. So it's the square of the first, x squared sine squared theta, square of the last, y squared cosine squared theta, minus twice the product of the two. That's our distance squared from the point mass that has coordinates x, y, and the axis, which has direction theta. So now, if instead we were trying to compute the moment of inertia about that axis defined by the vector u, we would take the distance squared for each mass, multiplied by dm, and add it up. So we're going to take that earlier expression we had for distance squared and insert it right here. Then using properties of the double integral, we'll pull out, for example, the integral of a sum is the sum of the integrals, so we can break this up into 3 integrals. And we're integrating with respect to x and y. So we can pull thetas out. And now we recognize something about these 3 integrals. The first one is cosine squared of theta times the moment of inertia about the x-axis. Now we're going to insert a double x down here. This moment of inertia about the y-axis. And finally, we have the product of inertia. So there is, if you know theta, your direction, and you know these 3 moments of inertia, then you can find the moment of inertia for that lamina about any axis. And that's what we say here. The moment of inertia can be determined by knowing those 3 things. Now, this expression right here can be rewritten in matrix form. We're calling u, and we'll go switch down to 2 dimensions now, which is okay. Calling u as cosine theta sine theta. Transpose of u gives us a row vector. We have this expression for moment of inertia can be written as u transpose this matrix times u. So if you carry out this multiplication, you will see what you have up here. Thus, we're defining this matrix right here as the moment of inertia matrix, or tensor. The moment of inertia matrix is a symmetric matrix, where this moment of inertia matrix is for a given lamina. You compute the moment of inertia with respect to the x-axis, compute the moment of inertia with respect to the y-axis, compute the product of inertia, and your matrix is formed this way. When you have an expression like this, u transpose I times u, that's referred to as a quadratic form. So let's look at an example. Suppose we define a lamina of rectangular shape where the base goes from 0 to 2. This is a lamina we saw in the opening screen. And the height goes from 0 to 1. Now, when computing the moments of inertia, this dm, we will assume that our lamina is homogeneous with a density of 1. So dm is dA, which is dx dy. So here's the computation of the moment of inertia with respect to the y-axis. Y goes from 0 to 1, x goes from 0 to 2, x squared, and that's equal to 8/3. The moment of inertia with respect to the x-axis, you insert y squared here and evaluate. 2/3. The product of inertia, you insert xy here and compute, and you get 1. So with those three values, we can construct the moment of inertia matrix or tensor. And here it is. For that particular lamina. Now, interestingly, Mathematica, we can determine the moment of inertia for some region by using this command, moment of inertia. It's the region we defined earlier, and it gives the same result. Now, to find the Now, we would like to find the moment of inertia about the line y equal to x for our given lamina. We first create our direction vector u, which is this vector right here. Then we compute the quadratic form. Now, up here, we are calling our moment of inertia matrix MOI. The uppercase I is a reserved symbol in Mathematica. So here I construct the quadratic form, U transpose times the matrix times U, and there it is. The moment of inertia for that rectangle about the line y equal to x is 2/3. This computation can be done using built-in Mathematica command called moment of inertia. We specify the region, we specify the direction, and it returns 2/3, confirming our computations. Again, Mathematica can compute moment of inertia matrices as such. Now, suppose we want to find the axis that will minimize the moment of inertia for a given lamina. Well, to do that, we need to minimize this quadratic form. And again, what we're changing here is find the direction u that makes this minimum. And we have a constraint in this problem in that u should be a unit vector. One way this can be done is by using the method of Lagrange multipliers. And we're going to have to take the gradient of this and set it equal to, we'll set it equal to a product lambda times the gradient of this. So computing the gradient of this quadratic form gives us 2I times u. And the gradient of our constraint is 2 times u. And Lagrange's method requires that this gradient be parallel, so we use some constant lambda here, times this. Dividing both sides by 2, we see to find the direction that minimizes the moment of inertia requires that we solve this equation, and this is a classic eigenvalue problem. In other words, the direction that minimizes the moment of inertia is one of the eigenvectors of this matrix. Specifically, it's the eigenvector associated with the smallest eigenvalue. The two eigenvectors for this matrix are referred to as the principal axis. Finally, we might mention, recall that linear momentum is mass times velocity. Angular momentum is computed using the moment of inertia matrix. So angular momentum, which we're going to use this uppercase L for, is the moment of inertia matrix times the angular velocity. Now here, we can see that the linear momentum is always in the same direction as the velocity. However, here, that's not true. The angular momentum is not necessarily in the same direction of omega as this is a matrix. However, if omega is the same direction as one of the eigenvectors for L, then these two will be parallel. That is, the angular momentum will be in the same direction as the angular velocity if your angular velocity vector is along one of the principal axes. But that's the subject of another video. Thank you for listening.